Okay. The conservation of energy says that energy is not created or destroyed. It's just transformed. So energy's not disappearing. It's just moving somewhere else. So all potential energy. Oh wait, hold on. Let's look at this situation. We're going to throw a ball in the air. It keeps all of its energy. It's just being transformed everywhere it moves. So when we throw it all the way up top, it's got all of its potential energy because it's as high as it can go. It's not moving anymore. So there is no kinetic energy because you have to have motion to have kinetic energy. Thank you. Put that on my desk, please.
Yep, I'm gonna be here tomorrow to finish this one.
Great. And to take the next one. Oops. Oh, sorry, yes. If you don't... Okay, yesterday we talked about kinetic energy is related to motion. Potential energy is related to what? What gives something potential energy? Yeah, it's got to be up high. So something that has height has potential energy. Something that's in motion has kinetic energy. So our ball has been thrown all the way the high as it's going to go. For just a small amount of time, it stops moving. That's when it's got all of its potential energy. But then it's going to fall back down. And as it moves down, its potential energy got used up because it lost height. And it's already moved half of the motion it's going to do, so it also only has half of its kinetic energy. Once it gets to the bottom, we've got no height left. So no height, no potential energy. So this is all kinetic at the bottom, because as soon as you get back down, it's going to be thrown back up in the air. If you know how high it was at the top, you can calculate how fast it will be going, which is velocity. And kinetic energy, the formula uses velocity. And then once you go back up, as it's heading up, it's used half of its kinetic energy because it's halfway to where it's going, but it's only halfway up, so it only has half of its potential. And then if you know how fast it got thrown, you'll be able to use that information to find how high it will go. And this just keeps repeating. So in this example, if we're only transforming energy, then all of our kinetic energy will be the same as all of our potential energy. Because I can't destroy any. Use this so that you can still see the letters. Remember yesterday we talked about these formulas. Potential energy is mass times gravitational acceleration times height. Kinetic energy is 1/2 times the mass times velocity squared. So whatever we've got, all of our potential energy at the top is going to be worth the same amount of all of our kinetic energy at the bottom. Okay? They give us this example here, a 4 kilogram ball. Kilograms are the units for, mass. So our 4 kilogram ball is thrown up in the air. It reaches a height of 1.8 meters. What does that stand for? They told you. Height. So we've got mass and we've got height. How fast was it thrown? We can figure that out. What is how fast? What is that asking?
It's asking gravity.
Gravity is always in a constant, so it's not asking that. What's another word for how fast you're moving?
Speed.
Speed or velocity. So this is combining our two equations from yesterday into one. We've got height, we've got mass. Gravity is always 9.8, so you've always got that one. They used 10 here. When you're doing your work, please use 9.8. They want us to find velocity. So because of the law of conservation of energy, we know that potential energy is the same as kinetic energy, and we can plug these in to find that missing velocity. So if you notice here, before they plugged anything in, what did they do in this first section? We had potential equals kinetic, and then what was their next step? Yeah. On both sides of this equation, I'll go a little wonky there. We had mass. What would you need to do to cancel out mass from one side and move it to the other? Yeah, all of these numbers are multiplying each other. So if I divided mass on one side, I would divide it on the other side, and then they would just cancel each other out because they're on both sides. You can do that every time. Since mass is already on both sides, you can just go ahead and cancel it out. And then what we're actually working with here is the gravity times height will be 1/2 the velocity squared. The next thing they did, they didn't even plug any numbers in yet, but they moved this 1/2. So I'm going to write this over here. This looks like gravity times height equals 1/2 times velocity squared. What did they do to move 1/2? How do you undo a fraction? Yeah, fractions are just a division problem, so the opposite of that is multiplication. So they multiplied the 2 to cancel out the fraction, and then it has to go on the other side. And that's why they have this 2 times GH equals V squared. And then they started plugging things in. So G is always the 9.8. They used 10. And then we knew our height was 1.8. So we had 2 times 10 times 1.8. If you go ahead and do that multiplication, 2 times 18 ends up being, come on. Yeah, V squared equals 36. But then that V still has the second power on it. So we're not finished. What is the opposite of an exponent? A root, yeah? So to undo squared, you have to square root both sides. On my classroom calculators, you have to hit the second button to get the square root symbol. The square root of 36 is just 6. And then your unit for velocity is meters per second. Okay? Questions there? The bottom half of this page is talking about different types of energy and efficiency. Zoom that out. So, since we can't create or destroy energy, it doesn't always transform into the same types. We've got 6 different types listed here. So these energies are transforming into all these different forms. Thermal energy, no, let's start with Chemical energy is stored in chemical bonds. So your food that you make, plants, even batteries, even though they're electrical, the way the electricity is made is through chemicals. An example of that would just be wood. The chemical makeup of wood. And then if you switch that to thermal energy, thermal is always heat. Lots of things turn into thermal energy when you boil water, when you light things on fire. If you have enough friction, we've talked about your brakes. If your brakes are grinding while you slam them, they get hot because they're rubbing together. So lots of things end up releasing heat. So your wood would literally catch on fire. Nuclear energy is from radiation, fission or fusion. So if atoms are decaying, splitting, or fusing together, these are enormous amounts of energy. So like a nuclear bomb are devastating because there's so much energy that they're using. Here they're using that example as like a generator. I'm sorry, they left out nuclear. Just kidding. We'll come back to that one. You don't want to play with nuclear energy because there's not very many places for all of that energy to go without destroying things. Mechanical energy is work. So if something moves, or if it has a lot of potential energy, that's going to become work. That example is what they used for the generator. And then electrical energy is moving electrons. We'll talk more about electrons in chemistry. This is what we usually think of as energy, like when you turn on the lights, or the energy that powers your electric appliances. Here they're using, the generator would power the electricity in your house. And then the last one is radiant. This is light. Electromagnetic radiation from light bulbs or the sun. Photosynthesis is using the sun, radiant energy from the sun to grow plants. When you flip the switch, the light is actually an energy source. Okay, so these just keep turning into each other. They never go away. Unfortunately, they don't turn into each other perfectly. So this is not going to, all of your energy is not going to transform from the wood to the fire. Some of it seems to be lost. It's not actually lost, but it feels like it. It's friction. In this process, that friction is known as inefficiency because it's making things less efficient. You can't work as well because friction's taking some of the energy away. Also, and I think this is a typo. Input work is always more than output because friction takes some away. So scribble out that less. That's not true. Friction always takes a portion, so what you get out of something is less than what you put in. This was kind of surprising to me. Cars are about 15% efficient. We're wasting a lot of energy in our giant cars. Bikes, though, 95% efficient. Way to go, legs. And then there's a new formula for these. Efficiency is work out divided by work in. So You're just going to make a fraction, divide, and then after you've done the division, you'll multiply by 100 because we want this to be a percentage. Okay? So for the example down here, if you use 20 newtons to push a 15 newton object 3 meters, how efficient was your work? You only need work out and work in here. So what is the work in is what you've done. So what work, how much energy did you use to push this object? Yeah, the 20 newtons is your work in because it's what you've done. The work out is moving that thing. Okay, so you used 20 newtons to push a 15 newton object. So the 15 is what it took out, what you had to do, what you were moving. And then they went ahead and took the 3 meters, but you don't really need it. So your, oh yes you do. I lied. You do need the 3 meters because work, they gave you newtons. And work is in joules. So you have a problem within a problem here. How do you find work? What is the formula for work? Okay. Work is force times distance. So just kidding, you didn't need that 3. So you need to find the work for the 20 newton thing, which was 20 times 3. Which 20 times 3 is 60. And then you need to find the work out. So we had 15 newtons times 3. So work out is 45. And then these are the numbers you're putting in your fraction. The smaller one, the work out, always goes on top. So we had 45 joules divided by 60 joules. You're going to get a decimal for these because the bigger number is always on the bottom. That's fine. You're going to get a decimal and then multiply that by 100 to get a percent. So 45 divided by 60 got 0.75, but when you multiply that, it'll be 75%. So that missing 25% is what friction did. Okay? Everybody good? Oh, crap. Okay, on the back, oh my gosh. Let's go through these types of energy or definitions together. What is the definition of efficiency? Yeah, B, work out over work in, how good the machine is at transforming energy. The law of conservation of energy says what? Yeah. You can't lose or gain energy. It just transforms. Cannot be created or destroyed. A percent. We want to know the percent if a thing is efficient. And then a transformation is your last one there. Changing from one form to another. It'll look like an O. All right. Let's go through these what kind of energy in this box. If you've got a ball on top of a hill, it's going to be able to move, which is mechanical. I'm just going to use M. These all have different first letters, so. The energy in hydrogen, hydrogen is an atom. That's not very descriptive. Excuse me. Blech. Hydrogen is one of the main ingredients in nuclear weapons. So that one's actually nuclear. They split the atoms of the hydrogen to create the nuclear energy. So that one's weird. A clock. How do you power a clock? Electrical. Your stove is thermal. You use heat to cook your food. Uranium in reactors, also nuclear. Hydrogen bombs and uranium are not things we should play with. The energy stored in food, not radiant, it's chemical. So radiant is just light. So given off by the sun is radiant. If a car is driving 50 miles per hour, mechanical, it's moving. A fire's heat is thermal, and then a fire's light is radiant. So some things can have more than one type of energy. We can go ahead and talk about these two. What type of energy is used by a fire? So how do you create fire? This one's kind of weird. What? Specifically, though, to get a spark, what has to happen? It's one way to get this thing to.
Chemical?
It's chemical. If you're rubbing your sticks together, what you're trying to do is get the chemical reaction to happen. And then fire gives off what type of energy? Yeah, both of those, thermal and radiant. I don't know why I started doing that. And then what energy is transformed from what to what when you turn on a flashlight? We kind of talked about this. No, we talked. What's powering your flashlight? Electricity, electrical. Yes. Electrical. So the electricity turns on the light, which is radiant. Okay. You guys can go ahead and do that top one on your own. And then we'll do these equation ones. We'll come back to those because I want to make sure we have enough time. Sorry if you were watching the video. I forgot to hit resume recording, so copy this down and press pause. Before you go, here we've got, you're pushing a 20 Newton object. You have to push with 30 Newtons to do this. And it's asking how efficient is your work. So what do you need to do to find work You're going to divide, but before you do that, they gave you force, and you need to find work. So you've got which one is going to be in and which one's going to be out. Flip those. You always have to do more work than you're going to get out because of friction. So the 20 is the out. The 30 is what you used, what you put in. You had to use 30 newtons to get this work done. But to find work, what is the formula for work? Okay, we're going to do that next, but I have to know, right now I just have force. What do you do with force to get work? Times distance, force times distance. So we have work in will be 30 times, we're moving this 3 meters. So 30 times 3 is 90, and then out is 20 newtons, also 3 meters, which will be 60. And then the efficiency is work. Ooh, which way is this? Work out, the smaller number on top, over work in, and then times that number by 100. Okay, so I want you to finish that one, and then go back and do these two and the definitions at the top, and then turn that one in when you're finished.